Hey everyone, today we're looking at whether a function is even, odd, or neither. So an even function is symmetrical across the y-axis. For example, if you have this quadratic graph that looks like it's been shifted down a couple of units, depending upon what the scaling is here, when you have a quadratic graph that's just been shifted either up or down, that quadratic graph will be an even function because, as you might remember, that graph will be symmetrical across the y-axis. So for example, if you take the graph and you fold it along the y-axis like that, this red dot would lie on top of this red dot, this blue dot would lie on top of this blue dot, but essentially every single point on the right side will lay on top of a point on the left side. So that's what symmetric across the y-axis means. So algebraically, you can verify whether or not a function is even by plugging negative x in everywhere you see x. And what you get when you simplify that is the original or given function. So it just takes you right back to the original, even if you plug in negative x everywhere you see x into the original function. So, and we'll do some examples down here kind of showing that. All right, an odd function is symmetrical across the origin, which really means a double reflection. Okay, so I don't think we've probably talked about this before in any other class. So it is kind of an interesting concept, but it is kind of like a twist of sorts. So essentially you take the graph and you like twist it, but it truly is a double reflection. So the twist is kind of hard to see sometimes, but the double reflect maybe be easier. So if you're just talking about like this piece of the graph, the piece that's where all x's are greater than or equal to 0. And if you think about folding over the y-axis, then of course that piece will then do this. And then if you take the graph and you flip it over the x-axis, then you might imagine that then it will turn upside down like it's supposed to get this piece of the graph. So essentially if you do a double reflect once over the y-axis and then once over the x-axis, this piece will lie on top of this piece. So the blue piece, the blue point here will end up here, the red piece here will end up here. But you can kind of see that would be like a twist of sorts of the function. So I've seen it kind of called both ways. So you can verify if a function is odd by same as you did with the even, plug in negative x everywhere you see x, except for odd functions, what you'll get after you clean up is you will get a situation where you have the original function, but the negative version of it. So meaning that the sign on every single term of the original function changes. Okay, so and again, we're going to talk about that here in a minute in the examples, and hopefully that'll be more clear, but this is what you need to jot down on your paper real quick. All right, so let's get to some examples. So determine whether the function is even, odd, or neither, then describe the symmetry. Okay, so look at number 1. We have f of x equals x squared minus x to the 4th. All right, so what we're going to do is we're going to compute f of negative x. So that means everywhere we see x, we're replacing it with negative x. So this x becomes negative x squared minus this x becomes negative x raised to the 4th. So everywhere I saw x, I replaced it with negative x. Now let's clean up. Okay. So negative x squared would just turn to positive x squared. The minus drags down, and then negative x raised to the 4th. Remember when you raise to an even power, of course, you're going to get a positive value, but that negative from here just dragged down. So look at the result. So there's no more cleaning up I can do. Now look at the result and see if you have either this situation or this situation. Do you have the original function? Or do you have a situation where every single sign has changed on every single term? Or do you have a situation where it's neither of those? Well, compare this to the original function. So how does this compare to the original? Well, it's the exact same. This is the original or given function. Yes, so it's the same. It's the original given function. So therefore, f of x is even. It is a even function because you got the same thing back out. Oh goodness. even. There we go. And then it tells us not only to determine even, odd, or neither, but then to describe the symmetry. So remember, even functions have y-axis symmetry. All right, so this right here is our answer. You're not going to box your work. You're just going to box your answer. And there you go. All right, number two. So again, same setup. You're going to plug in negative x everywhere you see x. So that's going to become negative x, the square root 2 minus negative x squared, and make sure and carry through that radical all the way through. Okay, let's clean up. So this, of course, when you multiply together is going to become negative 4x square root of 2. The minus is going to drag down. What happens when you square that negative x? It's just going to turn positive. So then there's no more cleaning up I can do. Let's go ahead and let's look at what we have. So do we have a situation where we have the exact same original given function? No. We have a situation where instead of this positive 4x, it's a negative 4x. What's under the radical stayed the same. So we know it's not even because it didn't stay exactly the same. So now the question is it odd or neither? And this one is tricky because you need to know if the sign changed on every single term. And in order to know that, you need to know how many terms were there even to begin with. And this one's so tricky because you would think that like there's multiple terms here, but this whole thing is joined by multiplication to this whole thing, which when you're joined by multiplication and not addition and subtraction, then that means that's a single term. So this is just one term. I know, so weird. So since we just have one term, all that we need is for that one term to switch signs, and it did. It became negative and the inside here stayed the same. So in this situation, what we say is odd, because that one term that we had changed signs, so odd, and because it's odd, we have origin symmetry. Okay, and I'm not really sure what we could put here. We could say sign changed on every term, which I know is weird because there was only one term, but sign changed on every term. So therefore odd function with origin symmetry. Okay, let's look at number 3. So on number 3, everywhere we see x, we're plugging in negative x. All right, so this will become negative x cubed plus 1. So let's clean up. Okay, when you cube a negative number, it remains negative. So this will be negative x cubed. The plus 1 will drag down. So then there's no more cleaning up I can do. Let's go ahead and analyze. What do we have? Do we have the given function? Do we have a situation where the sign changed on every term? No, actually, hopefully you're writing with erasable, because actually how I want to do this is I want to say this piece right here, sign changed sign. Okay, but this piece right here, if you're looking at the original, that changed sign, this did not. Sign did not change. Sign did not change. So remember, in order to be even, you have to end up with the exact same original function, which we definitely did not, because that term is negative. And in order to be odd, the sign has to change on every single term, and it did not. So what does that mean? It's not even, it's not odd, so it's a neither situation. So in that case, we're not going to indicate symmetry because there probably is not any. Okay, let's look at number 4. Okay, plug in negative x everywhere you see x. So negative x fifth, negative 2, negative x to the 4th, plus negative x minus 2. Alrighty, so let's clean up. So again, a negative to an odd power will remain negative. In this case, this negative to the even power will turn positive. So you have a positive x to the fourth times a negative 2, so negative 2x to the fourth. This plus negative x will turn to minus x, of course, because a positive times a negative makes negative, and the minus 2 drags down. So again, you can go through and analyze every single term and notice that this term changed signs, this term stayed the same, this term changed signs, this term stayed the same. Okay, so I'm not going to list that out. We're just going to talk about it. And then we're going to say, okay, well, since that happened, that is a neither situation. So neither. Oops, I didn't change colors here, did I? That's going to bother me. So I think I'm going to go ahead and change it so that way I'm not bothered. Okay, neither here. All right, let's look at number 5. Okay, on number 5, we've got to plug in negative x everywhere we see x. So we've got negative 3, this negative x raised to the 4/5. So we're getting some good practice with our rational exponents. Remember that word rational just means ratio, which really means fraction. So let's refresh how we tackle that. So remember that we can convert that rational exponent to a radical. So the negative 3 is not being raised to the 4/5, right? That 4/5 only belongs to the x. So it's only the x that's affected. So remember, top dog in the house, bottom dog outside. So this is like a 5th root of negative x. Goodness, that negative and that x is kind of connected there. It doesn't look right. So negative x raised to the 4th. Okay, so we've got negative 3, 5th root of negative x raised to the 4th. So let's clean this up. Okay, we know, again, that a negative number raised to an even power is going to turn positive. So this is positive x to the 4th. Okay, so now I think that's all we could do to kind of clean up, get rid of the parentheses, clean up as best we can. Let's go back to a rational exponent only to be able to compare it to the original given function. Okay, so if we convert back to a rational exponent, remember that would be the 4/5 power. Okay, it's kind of low. I know I'm being real particular today. Okay, so 4/5 power. Alrighty, so compare that to the original. What's it look like? Okay, it looks like exactly the same situation. It looks exactly the same as the given. So what does that mean? That means we have an even function, and that would mean y-axis symmetry. All right, that's it for today. See you real soon. Have a great rest of your day.